and we're going to do problem 10.5, where we have to look at these half reactions to see how many electrons we're using in each reaction. And if we do the example problem, that'll help us see what we're talking about. So problem 10.5 in our book, we want to estimate the percent available chlorine in chlorinated lime, calcium hypochlorite here. So where's calcium hypochlorite? Here it is, CaOCl2. Notice that there is a difference here. I think in a homework problem or a test question or something, people were confused between these two. This one has 2 chlorine atoms and only 1 oxygen. This one's got 2 oxygens and 2 chlorine atoms. Okay, so be careful there. When you're go ahead and hit the lights for us, Jason. Again. So estimate the percent available chlorine here. Don't I have my black pen? Did I use my black? There it is, right there. All right, percent available chlorine. Okay, so in table 10-1, Cl2 gas plus 2 electrons gives you 2 Cl minus. And that means the equivalent weight of Cl2 is the gram molecular weight of Cl2 divided by the number of electrons. And that's 2 times 35.5 grams per mole. 1 chlorine atom is 35.5 grams per mole, so we have 2 of them. Divided by 2 equivalents per mole, and we see that here. 1 mole of Cl2 has 2 equivalents in it. 2 electrons come off of that. And so we get 35.5 grams per equivalent. Then, also from table 10.1, we have CaOCl2 plus 2 electrons gives us 2 Cl minus plus CaO. And the equivalent weight here is going to be the gram molecular weight of calcium hypochlorite. I'm sorry, that's not calcium hypochlorite, chlorinated lime, divided by the number of electrons in that one, and that's going to be 127 grams per mole, divided by 2 equivalents per mole, and that is 63.5 grams per equivalent. So the percent available chlorine is going to be our 35.5 grams per equivalent divided by the 63.5 grams per equivalent times 100%, and that's 55.9%. Okay. You can also look at example 10.2 in your book to see this percent available chlorine. Basically, all this is saying is if I use 1 kilogram of this, it's going to be 55.9% as strong as 1 kilogram of free chlorine gas. All right? It's really talking about the mass. It's a mass per mass. It's got grams per equivalent over grams per equivalent in this equation here. So the question then is it possible for something to have greater than 100% available chlorine? What's your guess? Ellen, what's your guess?
We'll say no.
Why is that?
It's happening greater than 100%.
Exactly, yeah. Which is why this is really a bad concept, because you actually can have greater than 100% available chlorine. Or it's not a bad concept, the concept is fine, but I wish they used a different term. Unfortunately, this is the term they use. is percent available chlorine. Because you could have something that's stronger than chlorine, that's a more powerful oxidant, and it's going to have something like 80 grams per equivalent. And since chlorine has only 35.5 is the chlorine, right? So if you have something that's a stronger oxidant, you're going to get more equivalents with less grams. So let's say it was 15 grams per equivalent. Then that would make this greater than 100%. And the percent available chlorine would be greater than 100. So this is just a working or an operational definition to compare two chemicals. It's not actually saying how much chlorine is in this chemical. It's saying how does this chemical compare to chlorine. So maybe let's change the name. What's a better name for this then?
Chlorine index.
The chlorine index. All right. The chlorine index. All right. I kind of like that term. Anyone have another term? Mike's like, no way. Chlorine index sounds good. Sounds good. I like that better because that's what we're doing. We're just comparing it. It's a unitless term. You know, we're talking percentages. We're just comparing to chlorine. All right. So if you want to keep it straight in your head, don't call it percent available chlorine. Call it the chlorine index. Lights again, please.